All right, next up is Al Scott with his astronomy news update.
Okay, greetings. So a couple stories for you this month. The first one may come as a shock. There's actually been a paper published from the International Space Station on science. So our $100 billion space experiment with a $2 billion experiment here that's called AMS. This is the Alpha Magnetic Spectrometer, which is an international magnet that they've stuck on the side of the ISS. It's well shielded though, so it doesn't actually orient the ISS like a tuning fork every time it goes around the Earth. It's a very heavy thing. It's actually a cosmic ray detector. And the reason it works better on the ISS than down here on Earth is because of the atmosphere. So this is one of the particular experiments that benefits by being up in space, because the atmosphere and the Earth's magnetic field don't protect it as much, don't protect the astronauts as much as well from the cosmic rays coming in at us from space. So the AMS has very precisely measured a small excess of high-energy cosmic ray positrons, which are antimatter. And it's measured them, it can actually measure the direction these are coming from, and they're coming from all over the sky. There's no particular single source to this. And what the investigators believe is that because of this, this could indicate the presence of dark matter, which, if it consists of weakly interacting massive particles, which are theorized to exist by some extensions of the standard model of physics, each of these weakly interacting massive particles are their own antiparticle, and when they bump into each other, they will annihilate and create high-energy positrons and electrons. And this is what they believe they may be detecting, although they're not sure. And this isn't actually the first time this has been detected. This is a verification of other satellite detections. But if you have a $2 billion experiment on a $100 billion spacecraft, you better publish something. So the AMS collects its data by recording the number of particles that pass through its collectors. It can measure the kind and the energy of the particles and the direction they're coming from, mass, velocity. So each one of these pieces of data is a particle event. Since its activation on May 19th, 2011, AMS has collected detailed information on more than 31 billion individual particle events and downlinked this data for study. This is more data on charged cosmic rays than has previously been collected in the history of human physics studies. AMS continues to collect data and will continue to refine the results, collecting about 1.4 billion particles every month. The dark matter signal that they expect to see, that it's been theorized to see, would show that the ratio of positrons, antimatter, to electrons should rise at higher energies, near the energy of these supposed WIMPs, weakly interacting massive particles. And then at higher energies, they should drop off precipitously because there's a certain mass associated with these things. AMS sees a rise in its data, but the drop-off, if it exists, seems to happen at higher energies than the experiment has so far searched, above 350 giga-electron volts, or 350 times the mass of the proton, for comparison. After 250 GeV, the experiment sees the spectrum appearing to plateau, but they need to collect more data to refine whether or not there's a drop-off. So stay tuned. There may be an interesting, I'm sure there's going to be more papers coming out, and there may be something actually to announce a discovery. So interesting news, potentially. My second item is on observational cosmology, a field that's been enabled over the past 20 years or so with a series of satellites measuring the microwave cosmic background. This actually, what you see here is an all-sky image composed by the Planck mission, which is a follow-on to WMAP, which is measuring the oscillations in the microwave background to extreme precision. If you look at the microwave background radiation, it's about 2.76 Kelvin in all directions. But on top of that, there is a dipole. In other words, it's a little bit warmer in one direction than the other, and that's because we're moving in one direction with respect to it. Our galaxy is moving towards a cluster of galaxies, and They have to take that off. Then they have to take off all the background from all the stars in our galaxy and all the dust in our galaxy. And what they're left with are these little oscillations, about 1 part in 10 to the 5th of the overall signal. And so they've been getting more and more precise and higher resolution at measuring these little oscillations. What these oscillations are effectively sound waves that were echoing through the plasma of the universe about 380,000 years after the Big Bang. And by looking at these sound waves, what you can tell is you can understand a little bit about the density and viscosity of the universe at that point in time. And what that tells you is it gives you information on the ratio of matter to dark matter and to photons and all these things that make up the universe. So you can have an idea. We know what temperature roughly the universe was, and we can see that it was about, at the time it decoupled, what happened was electrons and protons recombined, and the universe suddenly became transparent to radiation. It turned from a plasma to a neutral gas. And at that point, the light was no longer scattering. It was actually able to go straight after that point. And now we're seeing that light from the farthest reaches of the universe. And what we're seeing is this it's basically a plasma, what we're seeing, but it's several billion light years away, and it's been redshifted down from a temperature of 3,000 Kelvin to about 3 Kelvin. And so it's really interesting what this actually represents. And because they now have extreme precision, they can refine the theories of what the universe, of how the universe evolved and what it was made of. And you can see down here in the bottom, we have a little graphic of before Planck and after Planck. And what this does, you can't read it, but it's basically, it shows you the ratio of dark energy to dark matter to regular matter based on our analysis of the statistics of this image. And you can see that there's a little bit more regular matter, a little bit more dark matter, a little bit less dark energy, and their estimate of the age of the universe increased by about 800,000 years based on this data. Another thing that they found is that there are some things that aren't explained by our regular vanilla theories. There are some small deviations from what we expect to find based on our vanilla theories of the universe. It seems to be that there's still a little bit of asymmetry to the universe that isn't explained away. And from the Copernican principle and all we know about how the Big Bang theory should work, the universe should be the same in all directions. But it looks like there may be a variation in, between the north and the south half. It's a little bit warmer on one half of the image. And some of the structures here are larger than what could have been predicted based on our understanding. So there's potentially new physics that's going to come out of this. And now it's over to the theorists to try to see if they can massage theories to better fit this data and see if we can understand a little bit more about how the universe has evolved up till now. So that's the end. Thank you.
Al? Quick question can I have the pointer for a second?
Sure.
Now, this is probably a mapping artifact, but the human brain is really good at connecting patterns and stuff, and I'm just wondering, I've seen maps from the different satellites, but I've never noticed this as an artifact. And I'm just wondering, do you have any idea? Can you see the line there? It's almost like an equatorial line on that sphere there. Do you think that's a mapping artifact?
That's our galaxy.
That line is the plane of our galaxy?
Yeah.
Very cool.
They have to subtract out its effect. So there's going to be probably some residual there because you're looking at, 10 ripples of 1 part to the 10 to the minus 5. So the galaxy actually is a huge, they're 1,000 times more intense than the signal that they're looking at here. So any errors in subtracting out the stars and the dust
Oh, cool. Excellent.
create that
Thank you.
effect. You're welcome.
So our galaxy is positioned somewhere in the center then, eh? From the way the picture was taken.
It actually goes right across in a swath.
And we would be positioned then in the center of that picture.
Yeah, well, it's an all-sky image. So yeah, you're
Al, there was a lot of
it
talk
envelops
about,
us.
There was a lot of talk about it in the southeast corner. There was an area that's supposed to be empty. Can you explain that a little bit? Did you hear about that? The cold spot.
They have,
It's supposed to be an empty area. There's not much there.
there's a couple cold spots there. I mean, there's one right here in the middle, and there's one over here.
That's right.
One thing that they've what you can actually do is that, I mean, these are photons that are coming from the most distant part of the universe, and anything in the foreground will scatter them away. And if you don't correct for that, you basically end up with an anomalous cold spot. I mean, they've used these cold spots to detect previously unknown galaxy clusters. Just because they didn't know there was a galaxy cluster, they found a cold spot in the microwave. They said there must be a galaxy cluster there. Something's scattering the light out. So this, verifies that this is actually coming from the farthest reaches of the universe, because they found a foreground galaxy cluster where no one knew there was one just by looking at this background radiation.
Now, we're talking about the space station, that AMS.
Yes?
Is it possible that if we get Mark II, a new version, eventually, that it might help us rather than, I know this is probably state of the art right now, but let's say 5, 10 years from now, as things progress, we may be able to solve that faster with better equipment?
Perhaps. I mean, I'm not sure exactly what the upper energy range of this is. The thing is, we don't really know how massive dark energy particles are. I mean, if they fall within the range of this, as this has only been operating for a few months now, on to a year, it's going to refine the upper energy levels as it progresses over, it can operate for another 10 years, refining those upper energy levels, and we may start to see a more precipitous drop-off. It could also, these positrons could also be coming from positrons, the authors have said, or from neutron stars, pulsars. That's another potential source of it. Neutron star positrons wouldn't drop off precipitously at a particular energy because they're just being accelerated in random processes. So it'll be kind of a very smooth drop-off rather than a sharp drop-off. So they're looking for that high-energy drop-off, but they don't know where it occurs. This experiment took about 15 years to build. I don't think the ISS is going to be up there long enough for a new version to go up. But perhaps, another experiment, if they believe that, it's going to be 1,000 giga-electron volts, there's no reason to think that it's, within the range of this experiment. It could be, 5 times the energy range before we actually see anything. Okay,
Great,
thanks.
thanks, Al.